Today we begin a new chapter, and this chapter is on solidification of binary alloys. Now, the topics which are to be which we will be covering are listed here. We will first start with isomorphous system. We will define what it is, what is the cooling curve. We will also derive an expression which helps us to find out phase percentage, which is known as lever rule. Then we will make a distinction, look at what kind of material, say suppose an ideal, what is the ideal and what is a real solid solution. We will also know about, we have introduced a concept of free energy, which defines the stability of phase. We will see that how the stability of phase changes with composition. Then we will look at the solubility limit and 3 phase equilibrium, and under this some of the common 3 phase equilibrium we will take up as eutectic, peritectic, monotectic system. We will talk also about transformation that can occur in solid state, and under this we will consider a few cases like eutectoid, peritectoid, monotectoid system. Then we will try and look at how we can to interpret or how to construct complex binary phase diagram involving many of these transformation processes which are listed here. And until this we will consider that the solidification process proceeds in a very slow manner, so that at every point there is equilibrium is maintained, thermodynamic equilibrium is maintained. Then we will look at, if there is a departure from equilibrium, what kind of effect do we get in the process of solidification and the structure that evolves. We will talk about dendritic and columnar structure, and we propose to cover this in around 7 to 8 lectures. Now, first let us look at binary isomorphous system. Let us consider two metals A and B that are soluble in all proportion in both liquid and solid state. Now, we have looked at it earlier while dealing with crystal structure. When can this happen? In liquid state, the miscibility is well known. Most metals, they are soluble in each other in all proportion, and but in solid state only those metals, they are soluble in all proportion where certain conditions are satisfied, like both metals have same crystal structure, same valency, almost similar atomic size. So, these are the criteria which determines the extent of solubility of one metal in another. Now, let us consider an ideal case of two metals which are soluble in both liquid and solid state in all proportion. And we learnt about thermal analysis, and this is a powerful tool in determining the transformation processes in alloys. And let us look at the typical cooling curve of pure metal A. If here it is liquid, and as you start cooling, the solidification begins at this temperature, and after certain time, when solidification is complete, again it starts cooling down. But when the solidification proceeds, the temperature nearly remains unchanged, and this is the melting point of A. So, let us say we write it as d A. Similarly, metal B, if you cool, it also will have identical or similar cooling curve, and here the melting point, this step in the cooling curve indicates melting point, that is T B. Now, what happens if we mix up the two metal A and B in the liquid state? Now, in a liquid state, it is much easier to mix metal, because apart from diffusion, we did learn about, talked about diffusion primarily in solid state, and we found that diffusion is a very slow process of mixing in solid state. So, all alloys are made by melting and mixing, and when you mix, apart from diffusion, you can stir the metal, and then the diffusion, since the diffusion also depends on the state of the material, state of the matter. In liquid, the diffusivity is much higher. So, therefore, mixing is much faster, and once they are mixed in all proportion, and then you start cooling the metal, that alloy made up of A and B. And say if you look at that cooling curve, it may have behave something like this. It does not have a step as over here, and this solidification possibly will begin this alloy at a temperature which is little lower than, depending on the composition, lower than the melting point of A, and it will be completed, that process of solidification will be completed at a temperature will be little higher than the melting point of B. And so, this we can say that T L, we say that define that this is a temperature at which solidification begins, when crystals of an alloy alpha we say that this is a solid solution of B in A, or vice versa, whatever you may say. So, this is the solid solution which is forming, and so there will be a temperature range when both the phases can coexist, liquid and solid can coexist over a temperature range. And after the solidification is complete, it starts cooling almost maybe nearly same rate as this. So, by performing this experiment on an alloy, we can get two temperatures, T L and T S, and these are functions of composition. Both of these are function of composition. That means, we determine this particular case T L and T S, we determine for a particular composition, let us say 50% A, 50% B, 50% B. So, for this, so that means T L, this is a function of composition. So, also T S is also a function of composition, and here we conduct most entire experiment, because we are conducted at constant pressure, and we will consider that constant pressure to be 1 atmosphere, 1 atmosphere pressure, which is because most processing will be done at a fixed pressure. Now, having determined T L and T S for a given composition, we can repeat the same experiment for a set of alloys for different values of x, x1, x2 and all that. And then if we get this data and we plot it on a diagram like this, here this y axis is the temperature axis, x axis is the composition axis. So, let us say capital N B, this represents atom fraction B. Atom fraction B, it starts with 0, this is 1. We can also do it for weight fraction. Now, atom fraction B, and suppose we have done it for this alloy X. So, alloy X. So, this actually is the T L where, so this is the T L where the solidification begins, this is T S where solidification is completed. So, in fact, what you can think about is what you can do is you pick up a set of alloys. For each alloy you plot T L here, T S here, T L here, T S here, T L here, T S here, and say suppose this is your melting point, this is melting point of A, this is melting point of B, and this is composition or weight percent B or mole fraction B. So, this is 0 B, this is 100% B or 1 atom fraction is 0 here, atom fraction B is 1. And then if you join this, you get a diagram which says that above this temperature state of the material, it is liquid, it exists in entirely in liquid state, and below this T S temperature it exists in solid state. So, here it is solid and here it is liquid. So, the phase diagram gives us you can say that solidification range, describes the solidification range of an alloy, and in this case of a binary isomorphous system, this is a typical phase diagram. The T L line that represents the temperature at which solidification begins is called liquidus. This line is called liquidus, and the line which represents temperature at which solidification process is complete is called solidus. And now, here look at the solidification process of this alloy X. So, when the solidification begins here, it can be in equilibrium. So, some solid will precipitate out. What will be the composition of that solid? So, that liquid, from the liquid some solid will precipitate out, and this solidus line actually, if you draw an horizontal line, this signifies then alloy, this x 1, this represents the composition of the solid that precipitates out from the liquid, and mark this, this has lower concentration of B. Obviously, the liquid will get enriched in B. So, that means liquid will now start following this composition. As it cools down, composition of liquid will change along this, composition of solid will change along this. But we have seen that diffusivity, composition of a solid can change only by the process of diffusion. Now, in liquid state diffusivity is several order of magnitude higher. So, this composition change in liquid will be quite fast, but the composition change in solid will take time. So, now let us say that we can allow this alloy to cool in furnace or cool at a very slow rate. We call this slow rate as a equilibrium cooling rate. Under this condition, we give enough time for the composition of the solid to change and follow this particular line, and ultimately say somewhere at intermediate stage here we can draw another tri line, and here it represents at this particular temperature the composition of the liquid must have changed from its original composition from here to this point, and composition of the solid has changed along this line from this point to this point. And we will see later, it is also possible as the solidification process continues, here it is almost entirely liquid, here it is a part liquid, part solid, and similarly when the temperature approaches solidus, then the solid composition will also change along this line. It reaches the composition of the alloy, and virtually the liquid also composition also has changed and almost reached here. So, but point is that solid which is precipitated out here, that amount of liquid will be extremely small, virtually non-existent. So, if it cools under equilibrium condition, the amount of solid goes on increasing as the temperature goes down, and here and the initial composition of the solid is this, but as it cools down, composition of the solid keeps on changing, and when the entire solid composition reaches this, in that case the liquid virtually disappears and the solidification process is complete. Now, let us see, is it possible to estimate say some intermediate temperature, you have drawn a this tie line, and then is it possible to calculate from this diagram what is the amount of solid and liquid at this temperature. Now, let us say A represents, let us say, weight fraction of alpha, B represents weight fraction of liquid at this temperature, and x 1 represents atom fraction B in alpha. So, that means this is x 1, and x 2 represent atom fraction B in liquid. Now, what you can do? You can try and find out what is, see, the total amount of B in the alloy is x. X represents weight fraction B in the alloy. In that case, you can simply write this equation. So, A is the weight fraction alpha times the x 1 is the amount of B. So, multiply this by x 1. So, this is the amount of B in alpha, and this is x 2 is the liquid composition, and B is the weight fraction liquid. So, this product will give you the amount of B in liquid, and the both should add to x. And again this weight fraction A and B, they are related, A plus B equal to 1. So, if you just substitute here, say B you replace in terms of A, and you do a little bit of algebraic simplification, you will find A comes out to be x 2 minus x. So, look at what is x 2, x 2 is this and x is here. So, amount of A is proportional to this, and whereas x 2 minus x 1 is this entire length. So, this is proportional to, you can say, that entire amount 100%, you can say x 2 minus x 1 is the total amount. So, weight fraction alpha is equal to this, weight fraction alpha is proportional to this arm, and weight fraction, similarly you can show weight fraction of liquid is proportion to this arm. In fact, this is something which is very much similar to what you call in the case of a lever. Say basically imagine, say this is the tie line, you can say that this Q point is the fulcrum, you have a lever, and this weight fraction A represents weight fraction alpha over here, and this point we call it P Q R. Q is the fulcrum, P where this weight is applied, similarly R, and at this place this B is the weight of the liquid, and you balance both, take the moment. So, A over B equal to Q R over P Q. So, this is base. So, in fact, you can say that the expression which we derived here is also exactly similar. You can find out for B also there will be a similar expression, take the ratio A over B, then what you get is this. So, that is why this rule in phase transformation or is often known as lever rule, and we will apply this to any of these phase transformation processes wherever the transition takes place from one phase to another over a temperature range. This helps you to find out amount of or percentage of transformation or amount of a particular phase at any temperature. Now, let us see how does the structure evolve. Now, consider this alloy X here. Now, if it is at this temperature, as long as it is liquid, you can say it is uniform all through, and then when the solidification starts, you have crystals of alpha forming, and which is shown over here. Not that they develop all on a sudden, it will nucleate and grow, and this is a continuous process and takes place over the temperature range. And these number of these particles, they grow in size, new particles also nucleate, and they also will keep growing as the temperature cools down. And if you assume that cooling rate is a equilibrium cooling rate, whatever solid nucleates or forms at a particular temperature, its composition also keep on changing. So, that means it will composition is here, it is linear in B. As it cools down, it will become richer in B. So, that means B must diffuse from the liquid into the solid, and it must diffuse from the surface to the center, the core of the crystal. And this process, to allow this process to take place, you have to cool it very slowly, and ultimately you will have a structure something like this. You will have different crystals differently oriented, and they will be meeting along some boundaries called green boundary, and it may look like, if you look under microscope, it may appear something like this. And later on, as we proceed, we will look into the shape of these crystals later. Now, while dealing on with solidification of pure metal, we introduced the concept of phase rule, Gibbs phase rule. And what do we infer from Gibbs phase rule? Now, which is illustrated here. Gibbs phase rule, it is stated as P plus F equal to C plus 1 at constant pressure. Now, here P is the number of phases, C is the number of component, and F is the degree of freedom. Now, we are considering a binary alloy. Binary alloy means number of component is 2. So, C is 2. So, C plus 1 is 3. So, degree of freedom is 3 minus P, that is number of phases which are coexisting. So, if you consider the system somewhere here, if you want to define a system, what is it made up of? So, you say that it is made up of liquid only, but in that case, to define the system, you need to fix up two value. It is not only enough to say define the state by stating that it is liquid. You have to say that liquid and its temperature is, let us say, T, which is given here, its temperature and its composition. So, you have to define two variable to define the state. Now, suppose similarly, if you want to define a state somewhere here, if you define an alloy, you say it is a solid solution A, that does not mean it can meet anywhere, any alloy over this regime. So, you have to define here also a particular temperature and a particular composition. So, you need two variables to define the state completely. But what happens if we consider the case when two phases are coexisting? Say suppose somewhere here. Here two phases are coexisting. In that case, what you need to define is, say the two phases are coexisting and the temperature you define, this is the temperature. Then automatically the composition of phases which are in equilibrium, they are fixed. So, one is this composition, another is this. So, in fact, if we look at it here. So, in this particular case, you see, if you say that my alloy is at a temperature and this temperature, and it is made up of two phases, then automatically phase alpha will have this composition, let us say x 1, and this will have a composition x 2. So, you cannot have an alpha of any intermediate composition existing here. So, this is what you infer from phase rule. Now, let us look at the free energy composition diagram. Now, we know that free energy of a solid solution is given is a function of its composition, and for an ideal solid solution we know that free energy of mixing is given by this expression. This is R is the universal gas constant, this is the temperature, this is atom fraction of A, and this is natural log ln Na plus Nb ln Nb. And say let us consider this is any solution whether liquid or solid, this relation will be valid if the solution is ideal. And let us consider an ideal system, we will come back to it again. What do we mean by ideal system? Let us consider at this temperature the free energy composition diagram. Now, here if you try and to plot this free energy composition diagram, now this will come out to be here solid is stable, here solid is not stable. So, liquid will have lower free energy, and this diagram is something like this, whereas liquid will have lower free energy and the diagram is something like this. And the relationship is, you can say that what we are writing is a delta G of mixing. So, when you mix the two, this is what is happening, but because this is a temperature which is much above the melting point of A, which has a higher melting point. So, here pure metal, here that free energy of alpha or A will be higher than free energy of a liquid. So, liquid has a lower free energy, here liquid is stable, same as in this case as well. Now, this is a schematic diagram, it is not to scale. And now, what happens if you come to an intermediate temperature range? Intermediate temperature range, something like this happens, the shape of this plot it changes, it is something like this, this is some, and this is the free energy diagram of the liquid. And in a free energy plot, if you draw a tangent, then this intercept is known as, say usually free energy it is 0 will be somewhere here, this is down. So, this intercept will be known as, you can say chemical potential, or you can say partial molal free energy. And this is partial, if you draw a tangent to alpha at this point, we will say that is the chemical potential of A in alpha. Similarly, if you draw a tangent here, you can also get a chemical, and let it intersect this axis, you will get chemical potential of A in liquid, and under equilibrium the potential they are equal, which is stated over here, mu A alpha equal to mu A liquid. Similarly, it will be followed for B as well. Now, this concept is simple, but let us try and see that if we consider the alloy system to be ideal, then how can we estimate or calculate this phase diagram? Is it possible to calculate the phase diagram from the basic concepts, say, and let us go through this exercise. Now, let us say here what you need to do, you have to find out the chemical potential of the two of A and B in the two phases which are coexisting. Suppose we say that this is chemical potential of, let us say, A in alpha. You have to calculate, equate it to chemical potential of A in liquid. Now, here look at, when you do this calculation, it is necessary to use the same standard state. Here you can visualize solid solution of alpha being formed at this temperature T. T is the temperature. Now, this you can say easily, you know that pure A, that is solid at temperature T, it goes into solution, we call this solution alpha, which is also solid. So, here you can easily say that your chemical potential of A in alpha equal to, that is the free energy of mixing or partial molal free energy of A in alpha, ln activity or mole fraction A. Now, how do you calculate the same thing in the case of, how do you estimate this? So, this is easy, this is done, but how do you get this? Now, here you can visualize, you have to use the same standard state. We have used the standard state here, pure A at temperature T. So, here if you consider pure A at temperature T, this has to be transformed into liquid, this is transformed into liquid, and A liquid goes into solid solution, it forms alpha. So, here you can say, so this is R T ln A in liquid, this is easy. And then how do you calculate the free energy change over here? This free energy change can be estimated. We know that free energy is made up of two component, delta H enthalpy minus T delta S. Now, at melting point of pure A, you know this is 0 at melting point, and let us say this delta H is enthalpy of melting of A, this is minus this melting point of A delta S. So, you can calculate that delta S equal to delta H m A over T m A. So, this is what you substitute here, you get this. Now, you add the two, then what you get is R T ln n A in L plus this we call is delta m A, and this also you can write as delta T with reference to that melting point of A, temperature difference from here to here, this over melting point, and this is and this we have found out, this is equal to, this is mu A L. So, this is equal to R T ln n A alpha. So, or if you can simplify, what you can say that this is N A liquid, this is equal to delta H M A delta T M A over T suffix melting point of A, then R, and this is the temperature. So, this we can say this is some function, this is a function of some thermodynamic features of A. And we also remember that in any of these phases we can say that N A alpha, N B alpha, these are atom fraction, A in alpha, B in alpha, this is equal to 1. Similarly, N A L, N A B L, this also is 1. So, with these, therefore, it is possible to construct from the thermodynamic constants or thermodynamic parameter defining A and B, basically the enthalpy change in melting and melting point, this is what you need. Then you can reconstruct an equation, one equation like this and another equation which is given over here. This you can do exactly in the same way by equating what you need here. You need to equate this, repeat the same thing for chemical potential of B utri, B in alpha, B in liquid, and in this case you have to also select in the same way that appropriate standard state, and here you should select this as a standard state, that is pure B liquid at T as the standard state. With the same standard state you equate and formulate this equation, and if you solve you will get the equation which is shown here. And now it is very simple to set up a spreadsheet or say tabular a table, construct a table and calculate these values, let us say F A and F B for different temperatures. Having done that, you can convert it, you can try and solve and find out this. You can equate the two. These two, if you equate, you can eliminate one of the variable, you will get N B L. If you eliminate this, you just rewrite this expression and it is possible. See, what you need to do is you can always say that this is ln. So, one way is 1 minus, you convert the first one N B alpha, this is equal to exponential, let us say F A, this function, this, and times 1 minus. Similarly, the other one you can say that N B alpha equal to exponential this should be So, now here if you equate, you get one expression for, you get this as one function. Similarly, you can also get N B alpha also a functional form. So, so in fact, you have two equation, two unknown, and it can be solved, and this is what you can easily do on a spreadsheet, which is shown here. So, these are these constants which are listed here. The melting point, what you need to know the melting point, and let us say that melting point of A is 800 degree Kelvin. Enthalpy of melting, this is 30,000 joule per mole. Then melting point of B, you take 500 and this enthalpy you can then set it up in a spreadsheet, and you know that R is approximately 8.3 joule per mole per degree Kelvin. So, everything is known. So, what you can do is set up a spreadsheet and you calculate for various temperatures, say set up a table for T, it starts with 800, so maybe 20 degree interval, come down to 500. For each of these temperature, you calculate the function that from the thermodynamic parameter of A. Similarly, you calculate this from thermodynamic parameter of B, and then it is possible you can find out atom fraction of B in liquid. And you will see that same entire thing, if you just invert it, take a reciprocal. So, maybe if you calculate A minus A or something, and then you can get N B alpha, and this is what is shown here in the spreadsheet. And now, what you do, you plot, this is the composition, this is the liquidous composition, this is the solidus composition, and if you plot this, you get this type of phase diagram. Now, if you do it in a spreadsheet, it will be interesting to change some of these, do some sensitivity analysis, change the enthalpy of A, change the melting point of A and B, and see how what happens to the nature of this phase diagram. Now, here all this calculation has been done with the assumption that the solution is ideal, and ideal solution means we say that free energy of that activity which is effective concentration of the species A is equal to mole fraction A, whether it is in liquid or in solid. Similarly, we consider both this is similarly the activity of A in alpha equal to N A alpha. So, that means you have an ideal liquid solution and ideal solid solution, both are ideal. And in fact, this is the famous, I think you must have done this in thermodynamics. So, you plot axis in one axis, activity of B in this axis, activity, and this is the atom fraction B in this axis. So, here here this activity is 0, this is activity is 1, atom fraction of B is 0, atom fraction of B is 1, and that means if both are equal, that means this is the line which represents ideal solution. Now, in reality this is never happens and you get both positive and negative deviation. So, in one case here let us say you have activity means in one way you can say the effective concentration. Effective concentration is more than atom fraction B here. So, which is higher than this. Similarly, you can also have a situation where effective concentration of B is less than atom fraction B. In that case, you have a negative deviation. In the same way, you can plot over here the activity of A also. Here we have, and this I will leave it to you. So, maybe this axis, the straight line joining these 2 points, this will give activity of A, and then you will also have deviations, negative deviations. You can also think about a positive deviation. So, this is activity of A in alpha. So, this is here also it is a negative deviation, and here Na is 0 here, Na, this is Na 1. Now, this situation, when does it happen? Now, in a solid solution consisting of two metals A and B, if they are mixed in random. So, everywhere wherever you go, if the atom fraction A is exactly equal at the number of nearest neighbors, say suppose we say that if the crystal structure is FCC, you have 12 nearest neighbor. Now, suppose the alloy has 25% or 1/4 is 1/4 of these neighbors if they are A, and in that case we say that it is a random solid solution, and it's exactly its composition, local composition is matching that exact that is that number of atom it has, proportional to the number of atom it has. And this is pictorially shown in this next one. Say suppose here in this case, say suppose this is a 2D crystal. Now, this atom, let us say one is A, another is B. So, let us say this is A and red is B. So, if this is A, look at A has 4 nearest neighbor and it has some amount of B, but look at here the number of A atoms surrounding this is more than the number of B atoms which should have been present, at least say some of these should have been B. Whereas, locally some of these B atoms surrounding B, this also is more, that number of atoms which should surround B is more than what it should be. So, that means something similar is happening, some kind of redistribution has taken place in this material, we call this clustering, and when you have this clustering you have a positive deviation. So, that is number of A atoms surrounding A is more than what it should be. Other extreme case, look at here, this is A atom, they are surrounded by all B atom. although we know that there are some A atom here, but they are not the nearest neighbor. So, that means here you have a, and you see that there is a regularity of arrangement. So, that means it is ordering. So, in the ordering case you have the other kind of unlike neighbors, you have more unlike neighbor that like neighbor. So, this is the other extreme. So, this if you can go back, so that means this is what is happening. In one case you have more like number of atoms than actual. So, if you this is the composition, this should have been the atom fraction B, but actually you have more atom fraction B surrounding a B atom, whereas in the other extreme case you have less number of atom fraction B surrounding B atom. And we will know about this in later in little detail, but these are called, the one is called, this is called clustering. You have one kind of deviation, it is a reverse deviation in case of ordering. And most real solutions you will have a similarity, and you have a such a situation. In fact, we also talked about it during diffusion. We define a factor called activity coefficient, and in fact, which defines which gives you the effective number of local concentration, and we will learn about it as more in detail as we go through these lectures. So, today to sum up what we have done today, we have looked at the case of unlimited solubility in both liquid and solid state, and this type of system is called isomorphous system. We looked at the cooling curve of an alloy belonging to this particular system. We also looked at how from this cooling curve the phase diagram can be constructed, and this phase diagram tells us how the solidification proceeds, and in this case the condition that and this describes the process of solidification when thermodynamic equilibrium is maintained at every step. So, we can say that this can give you the structure of the alloy if it is cooled in an equilibrium, under an equilibrium condition. We also talked about lever rule, which helps us to derive and or calculate phase percentage at a given temperature, and this is a general rule, and we will be using it to phase diagram to interpret microstructure evolution. We also looked at thermodynamics of ideal solid solution, and using the concept of thermodynamics, using the concept of chemical potential, it is possible to calculate phase diagram from the thermodynamic properties of metal A and B. And we also talked about the deviation from ideality. And next class we will talk about cases where there is partial solubility, they are not miscible in all proportion, and what happens in such cases. Thank you.